are continuing with our thermodynamics. Now we're going to talk about entropy. And entropy is designated with the letter S. No idea, you guys, sorry. Entropy is the amount of disorder or randomness, okay? So if you think about like a solid is very, very rigid. The molecules are kind of set where they're at. They don't have much entropy. But in a gas, you know, where they're cruising all over, they have a lot more entropy. So again, it's based on their, what they call the state function, which you, if you watched the video before this, you saw that, okay? So if it has a negative delta S, okay, so the change in entropy, if it's negative, it means it's decreasing its entropy, so it's going from like a gas to a liquid. It doesn't have as much randomness or disorder, okay? If it has a positive delta S, okay, that means the entropy is increasing. So then you would be going like from a liquid to a gas. You know, they're going from somewhat a little bit disorder, but to a lot of disorder when you go to a gas, okay? So the second law of thermodynamics deals with entropy. The first law, another way they name it is Hess's law, if you got that from the video, that deals with entropy, okay? So entropy of a universe increases in any spontaneous process. So the natural thing to do is to get more random, okay? So you end up with these relationships, okay? If it's a reversible process, the change in disorder entropy for the universe, if you add the system and the surrounding together, they're going to equal 0. But if it's an irreversible process, when you can't go back, you know, you don't have the double arrow, if you think of that, then if your system and your surrounding, it's greater than 0, okay? And again, I'll show you some examples of this, okay? So, will entropy be positive or negative, and explain why? Okay, so if I dissolve sugar in tea, okay, it's going to be more positive because if you're taking sugar, which is a solid, and you're dissolving it in a liquid, it's going to be more disorientated. It's not going to be so rigid because the sugar is going to be smaller particles, and so they're going to be moving around more. Okay, if I form frost on a window pane, okay, it's going to be negative because if you think about it, the water, in order to form on your window, had to be in the gas form, in the air, hits your window, becomes a liquid, and then if it's cold enough, and we all know about that, then it becomes a solid, and then you got to scrape it off and get all mad because, ooh, it's a pain in the butt, right? But anyway, it goes from a gas where the molecules are moving around a lot, then to a liquid where they've come much closer together, aren't moving nearly as much, and then down to a solid where they're really rigid and there's very little disorder, okay? What if I take air and pump it into a tire? Okay, again, that's going to be negative, again, because you're taking that gas and you're taking those particles and you're putting them under pressure. You're keeping them in a smaller space so they can't be as random. They can't spread out as much. They can't be as much disordered. So if you increase pressure, you're going to decrease your entropy. If you increase volume, then it's going to have more space to run around, and then you would increase your entropy. So if you want to decrease your disorder, you can increase pressure or decrease volume, and just the opposite would increase your entropy. Okay? So if I want to look at an equation and figure that out, on this one I have calcium carbonate as a solid, and when it reacts I get calcium oxide, which is also solid, but then I get some gas here. Okay? So this is going to be, I'm going to have more entropy because again, I went from 1 mole of solid to a mole of solid, but a mole of gas. So if it would have been this to this and not, the no carbon dioxide, then it would have been the same. But in this case, because I add that gas, I'm going to be more disorganized, I guess you can call it, or they're going to run around more, they're going to be more random. Okay, on this one, I have nitrogen gas and hydrogen gas, and I end up with ammonia. Now this one's going to be negative, and the reason for that is over here I have 4 moles of gas. I have 1 mole here and 3 moles here. So this amount, and then I go down to this mole, I have less amount. These guys are going to combine to make molecules, so I have less particles basically running around. And if I have less particles, then I'm going to have less disorder. Okay, so the entropy, because you're going from 4 moles of my gas reactants to 2 moles, I have less, they combine to make more molecules, so you have less particles, so your entropy is going to decrease. Okay, so how do you calculate S? Well, same way as you do delta H or entropy. It's the delta S, the change in the products over the change in the reactants. And again, the numbers are in that chart, that thermodynamic chart I already gave you. So it's the same process, okay? So same one as the page before. Okay, what I'm going to do is I'm going to start with the NH3, okay? So I look it up, and I look up NH3, and its number is 193. And again, I have to multiply by 2 because there's 2 moles of it, okay? Over here, it's not like entropy. You remember if there were, single elements, there was 0. Bummer, right? But there's a number for them. And again, just look it up in the chart. Okay, so 192 is nitrogen. And then I have to take 3 moles of the hydrogen because there's a 3 in front. So multiply, divide, and you get subtract. There is no dividing. Sorry, you guys. Minus 199 joules per mole. Now that's an issue right here, you guys. Because if you remember, entropy is kilojoules, and this one's joules. And later on, we're going to use both of those numbers. So whenever you have to do a calculation with entropy and entropy, you're going to have to switch entropy to kilojoules. I know that's a pain. Why couldn't they all be in the same? And again, I'll show you that in a bit. All right, here we got hydrogen liquid to hydrogen gas. Okay, so again, I'm going to take the hydrogen gas, which is 189, and I'm going to take the hydrogen liquid, which is 70. Since there's no numbers in front, I don't have to multiply anything, so this one's pretty easy. So this one's a negative, and this one's a positive. Okay? So things to remember about entropy, I should say it right. Enthalpy is heat. Entropy is disorder. It's like, why couldn't they start with different letters, right? But anyway, entropy tends to increase when you have increases in temperature. And that makes sense because the particles are going to move around faster. If you have an increase in volume, they have more space to move around. And then if you have the number of independent moving particles, the more you have, the more disorder you're going to have. So again, when those other ones I showed you, like when it went from 4 moles to 2 moles, the reason why it was less, because again, you had less particles. Okay? So those are the things that increase disorder or entropy. Okay? The entropy change in the universe is composed of a system and its surroundings. So we're doing all the disorder. We got the system and the surroundings. Okay, so there is the formula. So all of the change of random disorder or delta S universe is equal to the system plus the surroundings. Okay, if it is a spontaneous process, if it's a process that occurs just by nature, you don't have to do anything to get it going, your delta S for the universe, this number right here is going to be positive. So when you're doing these calculations, let me go back one. Go back two. Since this one was positive, I know this is spontaneous. Since this one is negative, I know this one isn't. Okay? Go back to where it was. Sorry, bye. All right. So if you're trying to figure out the total entropy and spontaneity, because really that's what you're looking for. That's what these help you do, to figure out if a reaction is going to happen. Okay? Without you intervening and doing something. If you look at all of these crazy numbers, you don't have to know any of these crazy numbers. What we're really looking for is this on the bottom, okay? Because here we've got temperature, and we've got our entropy, and we need our heat. All of those are involved to figure out if a reaction is spontaneous. So they have something called Gibbs free energy, and what it is the change in entropy minus temperature and the change in entropy. So this is, you don't have to worry about all of this, but this is how they came up with this. Okay, so the change in, or to determine if something is spontaneous, we look at what they call Gibbs. I like to call it Gibbs because I'm a big fan of NCIS. So, Gibbs is the man. But anyway, if you want to figure out the Gibbs free energy, this is how you do it. Okay, so what is it? Okay, well, if your delta G, your Gibbs free energy, is negative, okay, the reaction is spontaneous. It's going to happen without you, making it happen. If it's 0, if you calculate the delta G and it's 0, it's at equilibrium. So in other words, it's moving forward and backward at the same rate. And if it's positive, okay, if the delta G is positive, then the reaction is non-spontaneous. In other words, it occurs in the reverse direction, but not the forward. So if you need this reaction to occur, you're going to have to do something. Okay? more on Gibbs. And again, I just like to call it Gibbs because, NCIS, he's my man. But the Gibbs free energy is the measure of potential energy of a system. So you can use this formula when you're calculating Gibbs. You can figure out how much energy is potentially in that system. Okay, he did that with the hand warmer, if you remember that. And then you can calculate, like he said, it produced so much heat. Is that enough? Is it going to warm your hands, or is it too much? Is it going to burn your hands? So you can calculate that. Okay, so when delta G is negative, the reaction is always spontaneous. So it's going to happen. If delta G is positive, the reaction is never spontaneous. So again, if you want something to happen, you're going to have to do something. You're going to have to change one of the standards. You're going to have to add pressure. You're going to have to add temperature. You're going to have to do something for the reaction to occur. Okay? And there's the equation which was on the before. So delta G, the Gibbs free energy, is the change in enthalpy, H, minus T, the temperature, and the change in entropy. Okay? Where are we at now? I think I will quit here. Okay? So we'll go, I think we'll have one more after this. All right, so that's where we'll quit on this part of the notes.